All right, so welcome back, and we're going to continue our discussion about PCA. I hope what we have done so far has given you a nice idea of how to use it and what it does. There's a really good question that came in over the break, which is what did the positive and negative directions in the eigenvectors actually mean? Will they affect in interpreting it? So, as I showed in this little demonstration earlier, when PCA, either through whatever technique it's using, eigenvalue decomposition or SVD, when it draws these principal components, it's a vector that, starting from the mean of the data point of data cloud, points in a certain direction. And what's really important is that it's telling you the axis of the major variance, and the second PC tells you the axis of the second most important variance. However, which direction is it facing in? Why does it face this way? Why doesn't it face the other the other way? What I tried to explain, Hank, is that it's very arbitrary which direction it faces. It depends on a whole bunch of things. It depends on which function for PCA you're using. Are you on a Mac or a Windows? Are you on an Intel computer or AMD or some other chipset, maybe M1 Silicon from Apple, whatever it is? It depends on what operating systems, libraries you're using. A whole bunch of stuff can really affect which direction principal components are facing in. So you cannot really assume that you can replicate this on somebody else's computer, even on your own computer, after like 1 year time or something like that. Okay. So unfortunately, the directions, it's not reliable. Does it affect the interpretation? Yes and no. In the example that I did so far, where was it? Here, I kind of said that the first principal component, because it's negative in every direction of these items, I decided to call it lightness. And somebody else pointed out to me that, hey, isn't that a little risky? Because I just said that those signs could be totally flipped if I'd run it another time on a different machine or something. Yes. So my suggestion to you is come up with a name for PC1, but don't depend on whether it's really negative or positive. I did do that truly for this example, just so nobody's confused why I'm calling it hefty when all the values are negative. But generally speaking, do try to give it a name that is somewhat independent of whether it's negative or positive. Okay. So Hank, I hope that helps answer your question. There's not too much more we can do about it. You're not going to get the same signs every time if you use a different function or a different operating system or something like that. Okay, so the important thing is that you have a good name for it in one of the directions that it faces in. All right. Excuse me. And in the importance of the opposite meaning will be the same. Okay. So sometimes I call it heftiness, sometimes I call it lightness. It's because I too cannot decide which one to exactly call it. Okay. All right. So, okay. Thank you, Hank. Thank you for the feedback. Okay, great. So let's move on. We saw this data-driven approach called parallel analysis to finding the number of dimensions that are possibly present. Okay. Oh, hold on a second. I'm looking for something here. Nope. I'm looking for this. Okay. Give me a second here. I'm also looking for window view. Participants. Okay. All right. So let me move on. How do we interpret these dimensions is what we're going to spend the rest of the time on. And I apologize, I'm going to go a little bit over time today. Really sorry about that, okay? So let's take a look. So let's just do a quick review, though, of what these data, scores, weights, what these things all mean, because it'll be important as we talk about interpretation, all right? So we mentioned that these eigenvectors are really the weights of our composite PC scores. So when I look at the PC scores, like I say, give me the scores, and here I'm using PR comp, give me the scores of this decathlon PCA, all right? These scores were really computed by a regression like this, if you will. In fact, the weights here, so we said these are the weights, W1 W's all the way through. So the weights of PC1, these are the weights of PC2, these are the weights of PC3. The weights, you can think of the weights as regression weights. You can think of them as regression coefficients, in that if we did a regression of PC1 over, in fact, do I do it somewhere here? No, I don't do it here. Let me do it on my computer here. Let me go to PCA composites, right? So we're going to look at deck PCA. We're going to look at the scores, okay? By the way, before I move on, if I look at the correlation of the scores, PC1, PC2, PC3, like these are the scores, right? These are the scores I'm seeing now, right? So if I look at the scores, they look like this. And actually, yeah, let me round it to 2 decimals. And here we are. This is the correlation matrix of all the scores. What's going on? So many zeros. Well, of course, because remember, the principal components are all 90 degrees to each other. They are like the first principal component goes one way, the second principal component is 90 degrees to it. The third principal component is 90 degrees in the third dimension. The fourth principal component is 90 degrees to all of them in the fourth dimension, whichever direction that is. So actually the correlation matrix is completely empty because they're all orthogonal to each other. They're all completely independent of each other. All right, so this is a demonstration that principal components pulls really eigenvectors at 90 degrees to each other, and you can see that in the scores. All right, so do I have a little regression here to kind of show you what goes on? Let me just see if I have it here. Yes. Okay, so let me kind of show this to you. So these DEX scaled is the scaled version of our original data set. So, and actually, let me run this through my favorite little piping function that I have now. All right, so this is my data set, the decathlon data set, but I have scaled it this time, okay? Because when I do PC, I'm going to pass it to its scaled anyway. So let me scale it and show you the original data scaled. 10 original dimensions, 33 athletes, but everything is centered and scaled. All right. Now, here's what I can do. I'm going to run a regression, and I'm going to regress PC1, the scores of PC1. So these are the scores. Let me capture the scores of PC1. All right, so PC1 is now these are the scores of PC1. So there's 33 athletes, and they have each have a score on PC1. And I'm going to regress PC1 scores over, this is a way of saying all of the data in the scaled decathlon data set. So I'm doing a fully standardized regression. PC1 scores regressed over all my original data items scaled. All right. And let me look at the coefficients of this regression, and I'm going to show it as a vector. These are the coefficients of PC1 scores regressed over all the original items. Do those numbers look familiar? Well, they should. They should, because these regression coefficients of PC1 scaled, regressed over the original items scaled, is the same thing as my PC1 eigenvector. It's the same numbers, minus 0.42, 0.39, 0.27, 0.21, so on and so forth. All right, so this is my first eigenvector, which tells you essentially that PC1 is a composite. It is an average, is a weighted average of the 10 original dimensions scaled, and the weights, the regression, are really the regression coefficients of this. All right. So that's another view of eigenvectors. So we've seen eigenvectors from many different angles now. We've seen it from the geometric perspective as a vector pointing through the space. We've seen it through kind of a linear algebra perspective. We're now seeing it from a regression perspective. Okay, so this is the weighted composites that we're creating for PC1, PC2, PC3. All right, cool. Now, let me make it even more abundantly clear. All these things are related to each other. So as you saw, the scores are related to the original data scaled using the eigenvectors, which are the weights, okay? And essentially what it is that my original data scaled is nothing more than the scores times the transpose of my weights, all right? And I can use this in some interesting ways to kind of like derive what these different things are. So for example, if I wanted to do it the other, so if I wanted to, let's start with this one. If I wanted to get the scores of PCA, then all I have to do is take, the scaled data set. I'm making it into a matrix because I'm going to do a matrix multiplication with the weights. Weights are the eigenvectors. Okay, so let me make sure these are loaded up. And when I multiply these together, I'm going to get numbers like, what is this? 1.73, 2.78, 1.87. Do those look familiar? Those are my scores of principal components. All right. So the relationship between the data, the weight, and the scores is a fairly obvious one. The scores are actually derived from multiplying the data by the eigenvectors. Multiplying the data by the eigenvectors, and you get your scores, right? So the scores are really just weighted sums, right? And similarly, of course, we could do the other way around for demonstration purposes. I don't know why you'd want to do this, but if I just had the scores and I took the transpose, if I just took my matrix of eigenvectors and just turned it 90 degrees, transposed it, and I did a matrix multiplication on them, I would end up with the original data. Let's try it out. Scores times T weights, all right? And now this gives me, and let me just take like the, let me do this. Let me pipe to my heart's content. I'm going to pipe this through round 2, and then I'm going to pipe that through head. So I just get like the first several rows. So this should be what my scaled original data looks like. It's the scores times the transpose of the weights. So let's do the same thing, but this time I'm just going to look at the actual scale of deck. All right, and I should get the same numbers. Ta-da! Right? So this brings me to a point that once I've done PCA, if I use all the components, like if I had 10-dimensional data here with Decathlon, if I use all 10 dimensions, I could perfectly reproduce the data. Okay. And let me do something more of a little bit more of a demonstration here. I'm going to make a function here that does what I just did. All right. It takes the scores times the weights and reproduces the data. I can just tell it what is the original data set and how many principal components to use to reproduce the data in this function. So what I'm doing is I'm taking the data that you're giving me, performing a PCA on it, getting the scores and the weights, multiplying the scores times the transpose of the weights. And I'm going to use and for the scores, I'm going to use just as many principal components as you tell me to use. So let me try that. I'm going to reproduce the scaled Decathlon data set using all 10 principal components. And then what I'll do is I'll look at the residuals, the difference between my original data, scaled, and the reproduced data. And let me plot it out for you. Whoop, zeros all the way through. It means that there is no difference between my original data and the reproduced data that I got from multiplying the scores and the weights together. So using PCA, I've got information that I can use to reproduce my original data set. All right. What if instead of using 10 dimensions, I just used 10 components, I just used 2 components? Then it looks a little bit like this. Now I've got residuals. Now I've got errors for these 33 athletes. For each of them, I'm either overestimating or underestimating their original score. By the way, I'm reproducing here the scores of 100 meters, just for the 100 meters event, okay? because if I reproduce all the dimensions, like, it's going to be hard to visualize. So I'm only reproducing for the 100 meters event all the original data. Okay. And now let me do this in an interactive way, right? So this are the residuals of me trying to reproduce the 100 meters data for the 33 athletes. And this time I'm using all 10 principal components. If I drop a principal component, like then I start getting noise. All right. And if I drop another principal component, I get noise. If I drop another one, now I'm getting more noise. Another one, more noise, more noise. Okay. So if I use all 10, life is good. But as I drop, especially the important ones, then I have a lot more error in trying to reproduce this original data. All right. So this is just a little demonstration, and the code, I made the code available here, which is that there is a relationship between the data, the scores, and the weights, because the scores are just computed. The scores are simply computed by the data times the weights. All right. And similarly, if you have the scores and the weights, you can reproduce the data, but it depends on how many principal components you use. If you use the scores of all 10, you'll perfectly reproduce it. If you use a fewer number, you will, of course, you will start having error. Okay. But it's up, but so these techniques can be used to kind of reproduce data from the PCA results. All right. So that's just a little demonstration I wanted to show you, and that concludes my discussion about composite measurement. And I hope you get a sense that PCA, the scores, are just a composite of my original items, just weighted in different ways. All right. And if I choose and I can choose how many principal components I'm going to use. All right. Okay, let's take a little stretch break, and then we will talk about interpretation, which is difficult. How do you interpret this stuff? This stuff is like by machines for machines. Okay, how are human beings possibly going to interpret what this means? Okay, because last week when we started talking about all this, we were talking about how many dimensions of athletic performance are there? What do they mean? But as we see, it's really hard to interpret what what the eigenvectors really mean, because the numbers don't really correspond to like what you and I think of as meaning. All right. So I'd like to take a look at how we try to find some meaning and interpretability from principal components. All right. And this is an increasing problem with all fields of data science, particularly AI and machine learning, which is, how do we understand what the hell's going on? Like, how does a human being understand what's actually happening? Because at the end of the day, we are responsible for what our algorithms do. No one's going to arrest the machine, but if I do a bad recommendation or I deny somebody something that they should have had, I'm liable. So I need to know what the machine is doing. So how do I interpret what these principal components are trying to do, what they mean, what am I missing out? All right. So let me talk about a couple of different ways of measuring things. So we talked about the composite way of when I have multiple items, I can reduce them in some way to make a composite, and that kind of captures like what I want. So in this simple example here, I think I used this example in class before, maybe last week, which is I have a car and I'm going to get it inspected, and they're going to inspect and repair it, and they're going to, tell me like how much it costs. So I'm interested in this concept called the potential cost of the car. How do I measure it? Well, I use a composite. So in composite measurement, what I could do is I could take some amount of the months past variable, some amount of the repair time variable. I could find some weights to kind of average them with and produce this weighted sum that is my composite score. Okay. How do I find these weights? I can use some expert understanding of the problem. I could use some kind of potentially some kind of regression technique, or I could use something like PCA or something, right? However, oftentimes we are trying to express concepts that are not easily added up numerically to create what we want. Like, for example, if we are a business and we want to know, like, how satisfied are our customers? We're interested in this thing called customer satisfaction, right? How do we measure customer satisfaction? Like, how satisfied is a customer? I mean, I can't measure it with a ruler. I can't measure it with a weighing scale. I mean, how do I measure satisfaction? That's kind of impossible. I don't even know what satisfaction even is. Like, it's a feeling, right? Like, how do I even measure that? Do I probe into their brain, take a blood sample? Like, what do I do? Unfortunately, those things are untenable because we can't go around taking, maybe CT scans or, fMRIs of all our customers. So all we can do is maybe ask them some questions and try to, like, that's the quick and dirty way of getting some feedback from them. And we can try to see how satisfied they are. Okay. So for example, we could ask customers for some feedback, like, a lot of the time when you use an online service or e-commerce service, or for example, when you do Zoom or Google Meet or Skype, at the end it tells you, hey, how would you rate today's video conference, 1 through 5, right? So I could ask them a question like that, like, how satisfied are you with the service you got from this company? So I could ask for some feedback like this, okay? The other thing I could do is I could measure something, maybe don't have to ask them a question. I could measure how often do they come to my website? How often do they use it, right? Like if somebody's using Zoom or Google Meet every day, well, they're probably not too dissatisfied with it because they're using it every day, all right? I mean, maybe they're forced to use it, but we can also assume they're not complaining about it and getting anyone to change using it. So these are different ways I could measure customer satisfaction. However, is it fair to say that customer satisfaction is just customers' feedback and how often they use? Like, can we just add those numbers together and get customer satisfaction? A lot of people are dissatisfied with this composite way of measuring things. They feel like, no, some things are not just like two things added up. It's something other than that. And there's another way of looking at measurement of concepts, which we call factor measurement. And in factor measurement, we say, no, the customer's feedback on how much they use my, e-commerce service, it's not, it doesn't, you can't add those up to tell me how satisfied they are. In fact, it's the other way around. If they are satisfied, then they will give me good feedback. If they're satisfied, then they will use it a lot. So it's not that these two things cannot be composed together to create satisfaction. It's actually satisfaction that causes feedback to happen. It's satisfaction that causes people to use the service more and more. This worldview, this is just a philosophical worldview of how to do measurement, and it's called a factor worldview. It says we should measure big concepts as factors rather than composites. There are two competing views of how to measure big concepts, particularly in the social sciences, but increasingly also in other sciences as well. All right. So I want to talk a little bit about like the factor worldview, because in some ways, in many ways, the factor worldview has a way of helping interpretation. So let me show you what that looks like using PCA. All right. So this time I'm going to run PCA. Where are we? Number 3, PCA, factors. Great. So let me clear up all this stuff that I'm doing here. All this stuff that I'm doing. Let's clear the plots. Let's clear the console. In fact, I don't need the plotting space. I just need the console. All right. So this time I'm going to use a package that is heavily used by social scientists when they use PCA. It's called psych. I suppose it stands for psychology. All right, because psychologists use this heavily. And okay, I'm going to load this decathlon data set for the 100th time. And let me run a principal components analysis using the psych package. And I'm using the psych package because it is designed to help social scientists interpret multidimensional data using PCA. I mean, it's got other techniques built into it, but it's got a really nice PCA function in it called principal. All right, it's called principal, and it comes from the psych package. So let me run this function you'll see that basically I'm going to call principal. I'm going to give it my data set. I have to tell it how many principal components I'm interested in. So let me say I'm interested in all 10. Okay, but maybe I looked at the scree plot, I'm only interested in 2 or 3. But for now, I'm going to tell it I'm interested in all 10 principal components. I'll tell you what rotate means later. And then I'll tell it, please compute the scores, because I may want to look at those later. All right. So here I am. I'm going to run that. And I'm going to call it decathlon PCA full. Full to me means I'm going to use the full data. I'm going to use, I'm always going to use the full data set. I'm going to look at all the principal components, all 10 principal components. All right. All right, great. And let me just take that object and I'm just going to like inspect that object. I'm just going to hit enter and see what it gives me. Bang, it gives me all this stuff. At first, it looks very similar to what I had before, right? I've got these PC1, PC2, PC3 vectors. I've got some stuff on the side here. I don't know what those are yet. And then it gives me like, yeah, the proportion, variance explained, etc., 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 right? So it seems to give me something very similar to what I had before with eigenvectors, eigenvalues, proportion, etc. But there's a difference. The principal function, because it knows that eigenvectors are so hard to interpret, it doesn't actually report eigenvectors. It reports something else. It reports what we call loadings. All right, so this is the word is loading. So these vectors are loading vectors. They're not eigenvectors anymore. All right. In fact, I don't know if I have it here still, the eigenvectors. Where is the eigenvectors of decathlon? The eigenvectors were quite different. It was like minus 0.42, 0.39, 0.27, etc., right? But these loadings are quite a bit different. All right. So these loadings are quite a bit different. So what are loadings and how do they help interpretation? Possibly. Well, I'll tell you first what they are, and then I'll tell you how they're kind of computed. So what loadings are is a simple correlation between a principal component and a measurement item. So this value, minus 0.77, that's the correlation of principal component 1 with the 100 meters data. All right? So it's telling me the first principal component has a fairly strong correlation with 100 meters. It's somehow strongly related to 100 meters. Okay. I didn't have this before with eigenvectors. The number that I got before, I'm sorry for the scrolling, the number that I had before, this minus 0.42, was not a correlation. It was a coefficient in a multiple regression. So it was this like WI1 coefficient in this big regression. And yeah, it was helpful to compare that with other things, but by itself, it didn't give me a strong sense of how PC1 and 100 meters were related. But by using correlations instead of weights or regression weights or eigenvectors, I get something that's a little bit more interpretable for me. When I ask, how is PC1, like what factors is it mostly related with? I can answer that by telling you which measurement items is it most related with. I can answer that by telling you a similar answer, which is which items is PC1 correlated with. And this tells me that PC1 has a heavy correlation with the 100 meters. It also has a strong correlation with 110 meters. And it has correlations with long jump and 400 meters, like fairly large ones. All right. And yeah, so pole vault, 100 meters, 400 meters, long jump, 100 meters. What do these sports all have in common? They appear to all be sprinting sports, not just running, because 1500 meters also requires you to run. The javelin requires you to run a little bit and then throw the javelin. Some of these others might require you to like walk or run or turn around or do something, but these are sprinting, and in English, sprinting means you run at maximum power. So when you run at maximum power, it's really these sports: pole vault, 110-meter hurdles, 400 meters, 100 meters, long jump, all right? So already I can see a little bit more meaning. I can see a little bit more, it's a little bit more interpretable for me already to use these correlations, all right? So that's a nice thing that I have at hand right now, okay? So loadings are helpful in this sense. Now, I said these are correlations, and the reason we can interpret them as correlations is for the following reason. Loadings are taking the factor worldview. In the factor worldview, customer satisfaction is not caused by customer feedback. Rather, how the customer gives you what feedback the customer gives you is caused by satisfaction. So really, in a causal diagram, the cause is satisfaction, the outcome is customer feedback. In this case, if I look at one of the principal components, let's take PC1. PC1 is some underlying dimension of athletic ability, and it's causing athletes to have either good or low performance in 100 meters. Since the causal arrow is going this way, and PC is the cause, and 100 meters is the outcome, we would write these relationships as a series of simple regressions. 100 meters regressed over PC. You see that? If I do that, then, and everything is scaled, then my regression coefficient, remember what regression coefficient is when everything is scaled? In a simple regression, only two variables, x and y. In a simple regression with only one independent variable, and if you scale the data like we are doing, the regression coefficient is the correlation of the two variables. So that's the reason that we can look at this loading as a correlation, is because it's pretty much like the regression coefficient of a simple regression, 100 meters only regressed over PC. So if we try to use PC to explain what 100 meter scores you're getting, all right? And by the way, we call these loadings, we call them the Greek letter lambda. Okay, so we call them lambdas. So this is the factor worldview, and that's also why you'll notice this principal function refers to them as like the n factorial, the number of factors you're interested in, not the number of components you're interested in. Okay. So how are these loadings computed? Like, do we literally get the PC scores and then regress 100 meters over it? Well, there's actually a simpler way to do it without using any scores, and there's a geometric way of doing it, which is really interesting. Which is you can take your original eigenvectors. Okay, you can take your original eigenvectors. Remember, like these eigenvectors that were up here. Excuse me. You can take these eigenvectors from principal components, and you can just multiply it by the square root of the eigenvalues, which is the standard deviation of each principal component. Because eigenvalue is the variance, the square root is the standard deviation, right? If you multiply these two things together, you're going to get the loading, all right? And similarly, if you take one of the, all right, okay? And because it's computed this way, if you take all the loadings of a principal component, do it the other way around, you square it and sum it up, you're going to end up with the original eigenvalue as well, all right? So this is the relationship between loadings and eigenvectors. There's two perspectives. From the regression perspective, eigenvectors, their values are like the weights in a multiple regression where we're regressing the principal component over all the original items. From the factor worldview, the causal arrows go the other way around, so the regressions are 100 meters regressed over PC, the explanatory variable, the independent variable. Long jump regressed over PC, the independent variable. That's how you get lambda. That's what the lambdas mean. But you don't have to really have the PC1, PC2 scores to compute the lambdas. You could do it this way. It's a long way. The easy way is just to multiply the eigenvectors by the square root of the eigenvalues. That gives you loadings right away. All right. I'm going to take a little break right here to see if we have any questions, either about what these loadings mean, why we compute the loadings this way, or the relationship with the eigenvectors again. Okay. I'm going to drink some water. I'm going to give you some chance to write down some questions if you have them. I've got one question, so I'll try to address it. Metab asks, are composite and factor measurements similar to reflective and formative in smart PLS? Yes and no, Metab. So Metab is asking about another technique of analysis called PLS, which we may see next week, actually. And maybe I'll get to it next week, Metab. How's that? Okay, let me get to it next week because they are related, but not in the way that the smart PLS software makes you think they're related, but they are related. Yes, and we'll see it next week. So I'm sorry, you have to come back again next week. Can't get rid of this class. All right. All right. Any other questions? So two different worldviews of how to measure things. One worldview is just add up things and weight them, and with the weights, and just together they will build this thing called our construct. The other worldview, the factor worldview, is no, the construct is something that came first, and all the stuff you're measuring, that's caused by the construct. All right. All right. So that's the factor worldview. All right. Now, here's the interesting thing. Do you remember in simple regressions, and the simple regression means when you have one independent variable, we said in a simple regression where the data is completely standardized, the regression coefficient will be the correlation of the two variables. We talked about that several weeks ago. Okay, and this correlation in regression is called R. Here we're calling it lambda because it's a factor loading and it's got a different name to it. But the loading is just the R, the small letter R for correlation in simple regression. Do you remember what variance explained is? Variance explained like how much of the variance of 100 meters does principal component explain? Because remember, in a regression, we're trying to explain the outcome variable. The variable the arrow is pointing to is the outcome variable. How much of the variance of 100 meters is explained by this principal component? Well, in a simple regression, the coefficient is small letter r, and the variance explained is just r squared. And indeed, if you want to know how well is 100 meters explained by PC1, the correlation is right here, minus 0.77. But if you want to know how much of the variance of 100 meters is explained by PC1, it's simply going to be this correlation squared. So if you square the correlation, you will get the variance explained of the items by the principal components. The reason that's important is because, generally speaking, one rule of thummy kind of thing is when you're doing a regression, you can ask, how much of this outcome variable is explained, how much the variance is explained by these independent variables, in this case only one, and how much is explained by error. And oftentimes usually we hope that the independent variables explains more than half of the variance of 100 meters. Okay? We hope the principal component can explain more than half the variance of the individual dimensions. If it doesn't, that means that the individual dimension is explained more by random error. So the reason I'm mentioning this is because if we want an r squared in a simple regression of 0.5 or higher, we need to have a correlation of 0.7 or higher. Because remember, 0.7, actually 0.707, squared is about 0.5. So when you have loadings of 0.7 or higher, it basically tells you that the items are more than half explained, their variance is more than half explained by the principal component. So generally, when we look at do principal components and we look at the factor view, we are usually interested in loadings higher than 0.7, because then it indicates that this principal component explains more than half of the variance of this item. Put another way, this item is more than half whatever this underlying dimension is. All right. That's why I was saying PC1 is largely explained by 100 meters, long jump. I'll skip 400 for now, 110 meters, pole vault. All right. And these are all running sports, sprinting sports, in fact. You have to run super fast. Okay. So that's how we can interpret PC1. We say which items does load on very well, well being above 0.7, so that we know that more than half of the items variance is explained. And that helps us in the interpretation of what PC1 is. What about PC2? PC2 seems to be, wow, have a strong correlation with shot put and discus throw. Do you remember those two sports? Those two sports, to the naive person, look like they have a very similar form. In both cases, you've got to spin around and throw an object, right? With shot put, you've got to like spin around and throw this ball. And with discus, you've got to spin around and throw a round, heavy stone or heavy round object, like this, right? They both involve like this rotation moment and throwing. So probably you need really good core strength and lower body strength, to like get that momentum going. So that's really cool. PC2 picks that up so nicely. It picks up that shot put and discus seem to require similar underlying athletic ability, because athletes who perform well in one perform well in the other. All right. And PC2 picks that up really well. So this is really interesting. We are already able to interpret this data set much, much better than when we look just at eigenvectors. Just by flipping our worldview, and in this case saying, no, these athletic performances are not causing, these sporting events are not causing you to have athletic ability. Rather, athletic ability is causing you to have good or bad scores in these sporting disciplines. All right. And now we can really start interpreting these things by looking at these loadings. All right. There's one or two questions here. Let me try to address them if I can. Yenu says, so can I say for those situations which are hard to measure, we should use factor measurement, while others we can use composite measurement? Yeah, so there's a couple of ways to do this, Yenu. One is things that you cannot measure directly, and you're just kind of measuring the symptoms of that thing. Many people will say you should prefer the factor worldview. Many people say that, not everyone agrees, but that's one way of looking at it, is that the factor worldview is really good for things which are not simply a sum of its parts. All right. I'll say more about that next week, so I don't want to overstate that right now, but I'll give you my usual answer. Just wait till next week. All right. I don't want to use up all your tuition money so quickly. Let's look at the next question. Can factor measurement be applied to all cases? Like in the repair case, the cost is not causing months to pass. Oh, what a great comment. Yeah, you're totally right. The cost of the car isn't making the months pass. That'll be ridiculous, right? It's actually the months pass and the repair time that is causing the cost. So that's exactly why there's this huge debate about which worldview to use for which type of concepts, because some things are really composited together and they're kind of, we say, artificial, because they're kind of human-made constructs. Like we decided potential cost, like, or I should say the repair people in the company, the mechanics, they're the ones who said, look, it's taking a lot of time to repair this car. You should have brought it in earlier. I'm going to charge you more. All right. So you're totally right. The causality kind of goes that way. All right. So yeah, that's a great point. Yeah. So that's exactly why you need to know both these worldviews. Thank you. Fantastic point. Okay. Halim asks, can we put n factor less than the number of column in our data set? Yes, you can, Halim, and I'll show you that in a moment. Okay. Hank asks, so if the loading is for explaining PC's meaning, then what are eigenvectors explaining? Frankly, Hank, eigenvectors, they don't really give good explanations for human beings. But eigenvectors are really good for reproducing data. Like if you have principal components and you have scores, you can reproduce data. Or you could, or I should say, if you have data and you've eigenvectors, you can produce the scores. That's what I mean to say. So eigenvectors are more like for data-driven reasons, like to produce the scores and things like that. And the factor loadings are more for interpretation. And it really helps when the phenomenon you're studying really does have this kind of causal direction that factors presume. All right, great. So I hope that answers your questions. So for any of you, if I have not answered your question, unless I told you I'm going to do it in a moment, then please you feel free to ask me more. Okay. Thank you. Great comments. Let's move on. We used loadings. So I've got one more little trick to show you, and this is like a mind-blowing trick. So I need you to take a deep breath and hold it, and I need you to breathe out slowly. Let's do it again. Take a deep breath, hold it, and breathe out slowly. Yes, this is like yoga. Actually, any kind of meditation will tell you to do this. It's not just yoga, okay? I don't think Indian people invented slow breathing, okay? So, let's calm our minds because what I'm going to show you is going to blow it. I think it blew my mind when I saw it, okay? So, let's take a challenge. The challenge is these loadings are nice and they're kind of interpretable, right? Even, by the way, PC3 has a nice loading as well. It's got one big loading, and that's for high jump. I love that. It tells you high jump is a really weird sport. It's not explained by sprinting ability. In fact, if you watch high jump, they're not sprinting up to the bar. They're kind of taking these long strides up to the bar. And it's not explained by like core strength. It's like this really unusual, and it's not just simply jumping because long jump also has jumping in it, and long jump doesn't. But high jump is this kind of really other type of thing. Okay, where is long jump? Okay, long jump is on. Okay, long jump is on PC. Oh no, not long jump. Excuse me. Where is? Wasn't there one more? No, no, no. Long jump does involve sprinting. Sorry. High jump. Is there anything else that is not well explained by these so far? 1,500 meters is a borderline to explain, not super well, okay? By the time we get to PC4, PC5, these are not really explaining anything very well, okay? Now, here's my challenge to you. These seem nice, but somebody is going to tell me, and thank God nobody asked me yet, because I wouldn't be able to like answer it right away, but somebody is going to potentially ask me, what about like this one? Is that close to 0.7 or is that far from 0.7? All right. So is that a good loading or a bad loading? It's just 0.02 away from 0.7, right? What about this one, minus 0.66? Just because it's not 0.7, we're not going to consider it part of PC1? That's kind of sucks. There's a lot of borderline values here, in fact, okay? There's a lot of stuff that's borderline. Like 0.71 is just 1 over 0.7, and we consider that. So while these are interpretable, there are still some borderline issues, and there's some lack of clarity, okay? There's still values of 0.6, 0.57, which are not tiny, okay? So we can interpret these, but not perfectly. So the challenge is this. Can we make these loadings even more interpretable than they are? Right? Because human beings love interpretations. We like to understand what's going on. And there is. But to explain the next technique to you, we've got to go thousands of miles away to Spain, I think. I can't remember where. And look at some art. Okay, so follow me as we look at some art for a moment. It's gonna be meaningful, I promise you. So I think this is in Spain. I can't remember where this is. There's this giant art exhibition, and it looks like this. It's a giant structure with these bags hanging from strings. Each of these bags is it's actually one of these boxing bags. It's a boxing bag, and there's like hundreds of boxing bags hanging from strings, and it's art. I know what you're thinking. Yeah, artists, life is so easy. Just hang some bags from strings and make money. Well, God, what are we doing? Okay. No, 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 no. Wait on. There's a meaning in this. But where's the meaning? See, the meaning, the reason we can't see the meaning in this is because we don't have the right perspective. We're not looking at it correctly. To understand what this art is trying to show and why it's using boxing bags, we've got to rotate this art installation. Well, you can't rotate it, it's huge. Maybe you just got to walk around it. We've got to walk around it to see what it means. Let's walk around. Follow me. We're going to walk around this art installation. I'll take my video camera with me. I'm going to fly to Spain first and walk around it, and let's see what it looks like. Okay, jump in the plane, go to Spain. Okay, if only it was that easy. Got to do quarantine. And here's the art installation. And let's ignore certain words on the screen. Here's the art installation on the left. Let's walk around it and see if we understand what this art is trying to show us. Okay, walking around it, walking around it. Do you see it? No, not yet, not yet. We got to keep walking around it. Walk around it, walk around it. The bags are coming together. Do you see it? Almost. Keep walking around it, keep walking around it, and bang, there it is. That's the arts. Okay, it's the actually it's for those of you. This is another reason I don't give the handouts away too early. It's my last slide. It's Muhammad Ali, portrayed in 3 dimensions with boxing bags. It's beautiful. It's brilliant, right? And you can see what it is now. You couldn't see what it was a moment ago, even though everything was exactly where it was before. You just needed to rotate it a little bit and look at it from the right direction. Okay? And this, what we just did, is called rotation. And rotation can change your perspective on an explanation and understand it a little bit better. Okay? So rotation is a geometric technique to kind of boost the interpretability of what we're seeing. So let's try to do some rotation and see what it possibly means. All right. And I'm going to start with I'm going to start with a different example, then I'll come back to the decathlon example. All right. So I'm going to take a look at this example. It's not the decathlon example. I want you to see 2 examples. So I'm going to start with this fictional example. I hope it doesn't confuse you more. Okay. In this fictional example, I have this data set where I have different wines, wine 1, wine 2, wine 3, like, Hongzhou. Okay, so like I have these different wines, and they have scores on these different dimensions called hedonic, means if you drink it, like how pleasing is it. So it's got a score of 14. For meat means, does this wine go very well with meat? For dessert means, does it go very well with desserts? Price is, how expensive is it, I suppose. Sugar is how much can you taste? Is it a sweet wine? Alcohol means, is there a lot of alcohol in the wine? And acidity means, does it taste like, do you taste like the acid, like the sourness of it? Okay, so these are different scores given by, I suppose, some experts on these different wines. And when we do principal components on it, let me show this to you. This is an interesting picture. It's not what you think it is. This is not the principal components on the original data. It's not, because remember, if it was the original data, these data points would say wine 1, wine 2, wine 3, wine 4, wine 5. So this is not the wines. These are not the 5 wines. These are the 1, 2, 3, 4, 5, 6, 7 dimensions on which we measured the wines. So what this figure is showing you is really, it's showing you like what is the correlation, if you will, of each of the loading, if you will, of each of these dimensions of measurement, alcohol, hedonic, for meat, acidity, for dessert, sugar, and price, relative to PC1 and PC2. So we're kind of seeing the loadings in a visual format here, okay? So for example, for meat should hopefully, well, we don't see the PC results here, but for meat has a negative correlation with PC1, a strong negative correlation with PC1, and a slight negative correlation with PC2, all right? And sugar has a almost zero but slightly negative correlation with PC1 and a very strong negative correlation with PC2. Okay, so you're seeing the loadings, like what is the correlation of the dimensions versus the principal components. And what you'll see here is that some things like price are somewhere in the middle of having a strong correlation with PC1, and it also has a strong negative correlation with PC2. So something like price would be hard to interpret because it will have a strong correlation with both PC1 and PC2. Positive in one, negative in the other, but it's a strong correlation with both. So it'll be very hard to interpret price. Okay? So how can we improve the interpretation? Here's what we can do. We can take our principal components and we can rotate them so that all the original dimensions are closer to one of the principal components than the other one. So for example, here price, now it appears to be, now that I've rotated the principal components, by the way, they're no longer, PC1 is now called RC1 because it's a rotated component. PC2 is called RC2 because I've just rotated the component relative to the original dimensions, not relative to the data. Well, it'll also be relative to the data, but I'm trying to maximize the loadings for some components and minimize it for other components. So in this case, for example, price, it's now much more strongly correlated with the rotated component 1 because you have to go a long way down RC1 to get to price, but it has a much smaller correlation with RC2. Okay? So by doing this rotation, we have improved the interpretability of price and the components. Notice we did not change the data. We did not change the principal components. We just rotated them relative to the original items. Okay? This is a view of, like we had on the left here, this is the new view. What I've done is, yes, some things may be a little bit harder to interpret than before now, but overall, everything is a little bit more correlated with one component than the other. All right? So this is called rotation, and it helps interpretation. And let me show you how using the decathlon data set. So you've seen one view of it. Let me show it to you exactly again, but using the decathlon data set that you're familiar with. Okay, let's take a look. So in the decathlon data set, let's try some rotations this time. So this time, Halim, your question, I'm going to do principal components on the decathlon data set. This time, I'm going to tell it, just ignore the last 8 principal components. I'm not interested in them, okay? I'm only interested in the first 2 because they were the most meaningful anyway. So I'm going to take the first 2 principal components. Why only the first 2? Because remember we did the parallel analysis before and it suggested the first 2. So I'm going to say just report the first 2. Of course, it's going to compute everything, but it's only going to report the first 2 principal components, all right? And when I take a look at this, this is what we saw before, all right? And what I'm going to do this time is I'm going to plot, oh, excuse me. I'm going to plot here the data relative to PC1 and PC2. As you can see, the data, it's some, the 0, 0 is about here. It's kind of like looking like this, okay? Now, I'm going to add the 33 athletes. I'm going to add their numbers to the plot. So here they are. These are the 33 athletes. You can see them on the screen. Handy dandy little text function that lets you plot words or numbers next to data points, okay? Let me show you another plot. Here, I'm plotting PC1 and PC2, not relative to the data, but relative to the original dimensions, all right? So now, do you see when I kind of look at these loadings, for example, right? 100 meter hurdles and 110 meter hurdles, they have a very negative correlation with PC1. Right? That's why they're back here. But they have very small correlations with PC2. Oh, excuse me, this one. That's why they're so close to the axis of PC2, because they're not very correlated with PC2. Okay. When we look at the loadings from this point of view, you can see now why some of them were harder or easier to interpret than others. All right. So, and you can see that at least according to these two principal components, a whole bunch of my original dimensions, like this big cluster up here, this cluster over here, these are kind of correlated with both PC1 and PC2. They're kind of out in the middle. To be able to interpret them, it'd be really nice if the principal components kind of ran closer to them. So what I'm going to do is I'm going to try to rotate these principal components so that they are still 90 degrees to each other, but they are kind of running through closer to the middle. Like I want these original items to come closer to the rotated components. And I want things like 1500 meters, 400 meters to come closer to the first two components. Because remember, things like 1500 meters, well, it's not great. Its explanation from PC1 and PC2 is not great. All right. Similar like for javelin, which is like out here somewhere. It's not great. All right. 400 meters is also, it's not above 0.7 positive or negative for PC1 or PC2. So it's not great. So how am I going to do that? How am I going to do this rotation? Well, I'm not going to go through the math of the rotation. All we have to do is run this principal components again. Decathlon data set 2 factors. This time I'm going to tell it I want to do a rotation. And I'm going to do a special type of rotation. There's many types of rotations. I'm going to use a rotation technique called Varimax. It basically rotates your principal components, but keeps them at 90 degrees to each other carefully. All right. So there we go. That's my deck PCA2 rotated. All right. Now, when I rotate them, let's see what happens. And I'll kind of show this to you first on screen, then we'll compare on the slides. Okay. Now that I've rotated them, this is the data according to RC1 and RC2, rotated component 1, rotated component 2. Does it look familiar to before? Let's see. Well, let me just go back a couple of screens here. Before the rotation, it looked like this. After the rotation, it looks like this. Actually, I can add the text to it. As you can see, the data has kind of also moved around like almost 180 degrees or something like that. Okay. And now I can plot my original, I can plot the rotated components against the original items. And what you see now is all the original dimensions are at least close or closer to one of the rotated components. Okay, 400 meters has come close. Well, these were already close, but these are now running right through them, right? So all of these, like discus and javelin, have all come closer to RC1 now. What does that give me? And by the way, I can take this. I can take these loadings, okay, and interpret them. So let me kind of show them to you here. So this was the original. These are the rotated loadings, okay? So the loadings have changed now. These were my earlier loadings. They look familiar, right? We've seen them before with the 10-dimensional example. It was the same loadings as before. And as you see, there were problems with shot put. Well, it was 0.78, but it was also very high on PC1. With 400 meters, it wasn't 0.7 on either. Javelin and 1500 wasn't 0.7 on either. Now, after rotating it, we begin to see the patterns a little bit more clearly. For example, earlier when we saw 100 meters, it had 0.77 to PC1, 0.24 to PC2. Now it's much more related to RC1 and almost 0 to RC2. So you'll see each of the original items has come closer to one of the components, and so it's got much more distinct pattern of correlations. We can see that 100 meters long jump, strong with RC1, almost 0 with RC2. Shot put, 0.91 now with RC2, very small with RC1, you see? So that's what rotation does. We try to use this technique to just take away, to give more meaning to one component and less to the other, all right? And 400 meters and 110, both strong on RC1 and much smaller now on RC2. Discus and javelin, maybe one of them is a little bit better now. Discus is like very strong with RC2 and almost 0 with RC1. Javelin, okay, still not 0.7, but at least its loading on RC1 is very small. 1500 meters, I'm sorry to say, we can't do anything about it with just two components. It's just not going to fit into this two-component worldview, all right? So this is what loading, this is what rotations does. Rotations takes your principal components and rotates them not relative to the data. I mean, it does move relative to the data, but its goal is to move them relative to the original items such that the original items line up closer to with one of the components than the other. And this greatly helps in interpretation because some items will suddenly become strongly loaded on one and weakly loaded on the other. And you can very clearly now say for almost all but two of our original items, we can very strongly say which component that relates to now. Okay. So this is rotation, and it's essentially a technique that we use to improve the interpretability of our loadings. All right. Now I should tell you a couple of things about rotation. It improves interpretability, makes it much easier now. You can see that yes, RC1, this component, is really about all the sports in which you have to run fast. In fact, like since the 1980s, people have gotten, like I remember Carl Lewis back in the day when I was tiny, got a gold medal in long jump and 100 meters, I think in the same Olympics. I can't, if anybody's as old as me, they can remember. So these sports are much similar to each other, all involve very good sprinting ability. Shot put, discus, javelin, they're all throwing sports. They require good grounding, core strength. So you see, the cool thing is now I can go to like sports experts, clearly not me, but I can go to a sports expert and start talking about these values on these things, and I can engage with the domain experts a little bit more about like what is really going on with this sport and that sport and this sport and that sports, okay? And I can do that really nicely now, and they can look at these numbers, I can look at these numbers, and we can make a very clear and clean story now, except for pole vault and 1500 meters. All right. Why? Because 1500 meters is not about sprinting. It's not about throwing. Pole vault is really interesting because pole vault, you've got to be able to sprint like crazy. Like you've got to be a very good sprinter. And yet, very good sprinters alone don't necessarily do well on pole vaults. Okay. So it's a sport which is a unique combination of these two things. It's a sport by itself. If any of you have friends who do pole vaulting, they will nod and say, yeah, pole vault is a very, very unique sport by itself. All right. Okay. Because there's a lot of technique and other things involved, which gets really crazy. All right. That's the story of rotation. Now, I should tell you, okay, I see a couple of question here. I should tell you that rotation is not really used in the world of prediction and other things. It's almost purely an interpretability tool. And that's really interesting. It's really meant to maximize human analysts' ability to interpret. Okay, it's the machines don't care about this stuff. It doesn't affect, it doesn't necessarily affect all the things that the computer is going to be interested in. It will produce for you like, different scores and things, but we don't really use it because it doesn't generate the correct set of scores and everything. But it does give you better interpretability power. But you have to remember a couple of things. One is these RC1, RC2, these are not principal components anymore. We call them rotated components. They're entirely for interpretation. All right? But it does help you answer the question, finally, how many important dimensions are there in athletic ability? Parallel analysis, Horn's parallel analysis tells us probably two. What are these two dimensions? If we want maximum understanding and interpretability, one seems to be about sprinting ability. The other seems to be about like all the stuff that requires like grounded throwing, like discus, pole vault, and javelin. Not pole vault, discus, shot put, and javelin. Okay. So we're able to now interpret these in much more interesting ways. There's a question here. I'm going to do it quickly because I've got one more slide, which is not going to take time. Can we use this idea to decide how to delete or group some unnecessary factors by using this model? Maybe should be merged to make one sport, to make a deduction. I am not going to go that far, Guild, because that is going to rely more on domain, on a lot of things, political as well as sports domain. I don't think we can answer some of those questions with data alone. Okay. But it does tell us at least that what is a decathlon doing? Is it measuring all different types of athletic ability? No. These are the two it's trying to measure. And in other countries, in other cultures, there might be other dimensions. Like maybe in Asia, there's like more like martial arts, maybe not captured very well by these dimensions, right? Or in other areas, like maybe yoga or something, not captured necessarily well by these. So now you can start telling us other types of stories, of descriptive stories of what is and is not captured by decathlon, what is and is not considered by these 10 sports in human athletic ability. Okay. Okay, I won't go too much further into interpretation because it's a computational stats class. Last slide, then I'm going to let you guys go. Okay, the last slide is when we ran these analysis, there was like, when I ran these analysis, like there was like often like, where was it? Deck, okay, this one. There was a couple of columns, a few columns I didn't explain, H2, U2, COM. They're really easy. Let me explain them very quickly what they are. I think you will understand them quite easily, hopefully. Okay. So H, it's not H2, it's actually H squared. And what it is it takes your loadings, and for a single original dimension, like 100 meters was an original dimension. So for one of your original dimensions, it basically, essentially, it's taking the square of the first of PC1 loading and the square of PC2 loading and just adding them together. Okay. And what this gives you, this 0.65, it tells you how much of the variance of 100 meters is explained by PC1 and PC2 at both these principal components. So we can see both these principal components combined explain about 0.65, 65%. This makes sense because remember I said this is a correlation, and in a simple regression, if you square the correlation, you'll get the variance explained. So we know that PC1 is explaining 77% of 100 meters. But when you combine PC1 and PC2, it's the story is a little bit excuse me, the variance, this is the correlation. If you square it, you will get the variance explained. If you want to know how much PC1 and PC2 combined do it, then you take the loadings squared and add it together. And so it basically tells you that, okay? So 65% of 100 meters is explained by PC1 and PC2. 0.77 squared is how much PC1 alone explains of 100 meters, okay? Which is about 50 something percent. So together, they explain about 65%. U2, or actually it's U, not U2, it's U squared, is uniqueness. It tells you it's just 1 minus commonality. So commonality tells you how much do these principal components explain of 100 meters. Uniqueness tells you how much it doesn't explain. It's the leftover variance, the error variance, if you will. So we call that uniqueness. And we say that 100 meters is not 35% of the variance of 100 meters is not explained by PC1, PC2. All right. If you ask principal to report more and more factors, by the time you get to like 10 factors, which means all the components, of course, you're going to explain everything. Your commonality will be 100%. All right. What else? I mentioned before that the SS loadings is just the sum squared of the loadings, and this really gives you the eigenvalues. All right. Notice that rotating the components doesn't increase our communality at all. We're not somehow magically explaining more of these dimensions, more of 100 meters by rotating. So rotating is only for interpretation. It's not like increasing our, variance explained or something like that. All right. Okay. And this is the last thing I wanted to put in your head. Rotated components are not principal components. Not. The loadings are different. The variance is explained can be different. The scores are different, but communality, when I say variance is explained, I mean the loading squared are different, the scores are different, but the communality, the overall explanation and measurement items of the measurement items the same, and the components remain orthogonal, at least with Varimax rotation. There's other types of rotation which can relax the 90-degree rule. Then what does the last column com mean? What does the last com mean? I don't remember. Let me get back to you on that. That's a great question. Okay, I really don't remember. So let me please get back to you. And if I've made a mistake, I'll let you know. Okay. All right. Cool. I'm going to stop it short here because I'm already 10 minutes over. Thank you. I'm so sorry that I have a hard time keeping to time with this online format because I've got to wait for you guys to type and it takes me longer to get your feedback. So thank you, everybody. I'll have one more assignment on PCA. Now that you have a little bit more understanding of it, you're a little bit more comfortable with it. Hopefully not. So this is my style. Whenever I give assignments, the first time I give an assignment is I want you to just play with it because we learned a new technique and just kind of learn how to drive the car. And then the next week, we kind of really dig deep into it, and then you can really enjoy what it means and how it works a little bit more, okay? So that's it for today. Thank you all very much. We have 2 more lectures. The next lecture does have a homework associated with it. That's week 16. Week 17 is an optional lecture. You don't have to come if you don't want to. It's me just telling you some more interesting things about coding and data science. Not really about statistics, it's more just about coding. So if you really like the coding aspect of the class, come to week 17, have a glass of wine with you because there's no homework associated with it. Enjoy, all right? And I will see you later, okay? Take care and bye-bye.